Action is necessary.
Good evening, everyone. My name is Raj, one of the founders of this KnowML Meetup group. This is our fifth, I guess, fifth Meetup group so far. We've been having great content, great discussion, and I'm really glad you all came and be part of this fifth KnowML transfer learning session we are going to have. Just a courtesy check. How many of you are familiar with ML, AI, have been working on it, and how many are enthusiasts? I guess everybody is enthusiastic. I'm Raj, as I said, and this is Lijesh. He is going to be our main speaker today, and Krishna. We three have formed this group, and our main goal is to actually build this ML/AI community within Dallas. We are also, building our own products. We are trying to go to different companies and try to market ourselves. So there's a lot going on. So yeah, thanks everyone for coming in and spending your valuable Thursday evening time. Welcome. Vijay.
Thank you, Raj.
Thank you. I see some of the faces from last time. Few faces, which is nice. So today, our topic today is to talk about transfer learning, and essentially, bulk of the content is to go to the paper on transfer learning, which was put out by Yan and Lang. So bulk of the content what we are discussing today is from that paper. So I think this picture out there kind of represents what we're going to talk about, right? Just like we humans do transfer or take our learning from one area and kind of apply it to another, how can we do it in the machine learning space? Right. And what we are going to talk about today is basically how can we use models which are built for different purpose, and take parts and pieces of it and build upon it to solve the use case which we have in front of us. So that's kind of the overall gist of what transfer learning is all about. So for those, I think in our last session we kind of went into discussion of deep learning, why deep learning, how is deep learning different from machine learning, right? And we kind of discussed it in detail. Today I just wanted to briefly touch base, the concept of deep learning, and then we'll get into how it is relevant for transfer learning, right? So again, especially the ones who attended last time, right, I will call upon you guys to kind of describe what a perceptron is. Want to try? Give it a try, Sagam?
I'm going to pass.
Okay. So at the simplest level, deep learning model is made up of perceptron, right? And just as this diagram shows up there, what you should take with you, the infusion of perceptron is, you apply a linear function, and then you apply a nonlinear activation, right? So in this case, if there are three inputs, which in this diagram is shown by x1, x2, and x3, you apply a linear function, right? And what's the linear function? Basic algebra, right? Y is equal to mx plus b, or y is equal to mx plus c. In some countries, we have thought constant as b or c, whatever, but that's the linear equation you apply. So what do you do by applying linear relation or equation? You are capturing the linear dependence between the input and the output. And then on top of that, you apply a nonlinear activation, which is to capture the nonlinear behavior of data. Right? As you would imagine, the relation between an input and output is not going to be always linear, but there is always going to be a non-linearity dependence between the input and output, and that is kind of captured in the non-linear portion of it. Again, I'm not going to talk in detail today because we did that in our meetup session, and if you want to definitely know more about it, like I was saying to you, it's posted on YouTube. Feel free to go and check it out. So these are a few of the non-linear functions we talked about in detail last time. The sigmoid function, the tanh function, and the ReLU function. And we talked about the equations as well. I'll skip over this and kind of get into this. So one of the questions I kind of asked last time is why is non-linearity needed? So if you were to think about a data distribution such as this, right, where green represents one class and red represents another class of output. In other words, give me a good example, Raj, for class distribution.
Learned population in a city or versus, uneducated people.
In any case, so imagine you have a distribution of data as such, where green represents one class and red represents another class. Definitely this kind of, if you were to put a model which captures only linear relationship, as you can imagine, this function cannot be built just by linear relationship, right? So the relationship is, can be well captured by. So if you were to draw a linear relationship, you'll probably end up building a function such as this, which in no way properly categorizes different classes of data. Right? That is why a non-linear behavior is needed in the model. So just to restate, the deep learning models are function approximators. They try to approximate a function. And every perceptron kind of tries to approximate a function for a specific feature. Right? So if you were to imagine layers of deep learning layers, then they incrementally build on the previous function. So it becomes a composite function for the inputs. If this intuition, if you're still not getting the intuition as you go through, you will kind of follow it, and we'll discuss it more. So with deep learning, so that was the data distribution. Because of the combination of linear and non-linear functions, you are able to now get a model which kind of can, model this behavior. And you are able to classify between two different sets in this. Does that make sense? Any questions? Anything we want to discuss further before we get any further?
I think is activation functions something we spoke about in the last meeting?
Yeah. The activation function, like I was saying, kind of captures the non-linear relationship, and it is for that reason that you can see those nice curves around the data set, right? So when your function is trying to cover the data, data boundary, right? Your non-activation function kind of brings in a non-linear relationship. As a result, instead of getting a straight line classification between two sets of data, now we are able to get a smooth curve to classify your data more correctly.
So how do you decide which activation function to use on what type of problem?
We did talk about it in detail last time. So yeah, that's a good question. There are different kinds of activation functions and we use it for different purposes, right? Like the one which I showed on this slide, right? There are quite a lot. Right? These are only among the few. So sigmoid function is typically used for binary classes. right? You have a male or female, for example, as an output, right? So you can use sigmoid function as the output layer, right? It outputs 0 or 1. So that's a binary classification. Hyperbolic or tan H, which is similar to a sigmoid function, right? It's a variation of it. The only difference is sigmoid kind of has a mean of 0.5, whereas tan H has a mean of 0. Now, ReLU is something which you use in your intermediate layers, in your hidden layers. And ReLU, the way it brings the non-linearity is works by the equation max of 0 to z, meaning any relationship which is captured as a negative kind of gets zeroed out. So we talked about what are the benefits of different functions of activation last time, and that itself is a topic, so I'm not going to get into that. It's not today's topic. So I just wanted to kind of bring some of this, basic concepts up, because these are kind of foundation into what we are going to talk about today. So right, so what I was discussing so far was just perceptron, which is one elliptical within the layer. Right, let's take A1 layer. So the top ellipse within it, that's a perceptron, right? So within, does everyone follow what's a perceptron? Just that one elliptical within a layer. So if you look at this is a very, very simple layer, just has two hidden layers and as an input and an output layer, right? So each perceptron kind of takes input from all the features, right? And it tries to approximate a function for that feature. Now, if you were to imagine all the perceptron in a layer, all of them are trying to approximate a certain function for a certain feature, right? So feature is the input, in this case x1 and x2. So you feed input, like for example, if I'm going to predict, write a model to predict the price of a house, right? I'm going to feed in a lot of input into it, like maybe the year the house was constructed, right? The square feet of the house, the zip code in where the house is located, right? And you can imagine, right? A lot of inputs which you can provide to the model, right? Deep learning model in a way is unique. It is able to extract information from the features, right? Unlike shallow learning, again we talked about it last time. Unlike shallow learning, deep learning is able to extract information from the inputs, and you don't necessarily have to prune your data in such a way that the model has to understand. Deep learning can understand, and the reason is because you have this different perceptrons, each of which is a function approximator. And as you can imagine, as we stack more layers on top of previous layers, the function approximation which was done in the previous layer is now, in a layer above, is further built into a function. So it's a stack of composite function, one over the other, and that's how any complex use case, if given input, if given enough data, can be solved by a deep learning model. We'll get into intuition further as we get into it, right? So let me at this point ask the question, right? So now imagine a model where you want to kind of predict the input picture which has been supplied, whether it's a picture of a president, US president, right? So that's a use case in front of you. what do you think is the data which you're going to kind of supply it? Okay, you'll supply it pictures, but what pictures? What kind of pictures?
Probably the difference between length of the difference between the eyes, the distance between mouth and.
Oh wow, this is too much. That's nice, but I think yeah, the picture of the president for sure, right? You want to supply all pictures of the president, right? What else? People who are not the president. Anything else you would need in terms of data? Awesome, different backgrounds, right? It's, if you change president in a different setting, it's a different picture, right? So you want to train your model to be able to recognize president in this case in different settings, right?
Age.
Say it again.
Age.
Age of?
Age of the person.
Okay. In what sense? Oh, different ages. Okay, that's a good point, right? Different ages as president has grown over the years. Yeah, this is really good. I was not thinking about that. But that's nice. But also resolution of the image, right? Image which you may have very high resolution, whereas you may get a blurred image, you may get a rotated image, you may get a sheared image, right? So you may want to think about what are the different combinations of image resolution itself you want to supply to your model, right? So that's good. Anything else?
Different expressions, profile.
Sure. If you have president in different poses, why not?
Selfies.
So okay. So if you were to imagine that model now, right? Now the intuition which I was kind of trying to give you was now we have this three-layer model, right? As this shows, right? The first layer is a function approximator on the image to try to understand the edges, right? Edges around the face. So now that's what the perceptron in the first layer is kind of trying to do, right? Very basic task as in where are my edges, right? In this, so it's learning that behavior. Now the next layer now, since it has got the edges, right? Now it is trying to learn combination of those edges, right? Hey, this is a nose, right? So it kind of learns. It kind of learns the composite function on top of the previous layer. Now, if you were to imagine a layer subsequent to that is trying to kind of identify maybe eyes, maybe nose, maybe hair, and so on, right? So as every layer gets stacked on each other, right? That's how model kind of learns, right? So it's just simple features are learned in the earlier layer. As the model gets deeper and deeper, the more composite features are learned in those layers. Does that give you some intuition of how the model, network works internally? Any question? Go ahead.
So in a linear learning model, you feed in an input, you say, let's say, same example, picture president. You feed an input, you say, this is picture president, this is picture president, this is not, this is yes. Do we have to do it in a deep learning and in every given line, like this is A, this is I, this is president, picture, this is not? Do we have to do that or just automatically do it?
There are different kinds of model, right, which I think we talked about in one of our very first session, which is like supervised learning, unsupervised learning, and so on, right? So in supervised learning, typically, which is what I'm talking about right now, right? You typically, have labels for your data, meaning when you train the model, you say, hey, this picture is a president versus this picture is not a president, right? Unlike linear models, right? The linear models like us I was showing earlier with an example, is limited by the fact that no matter how many layers you stack one upon another, the outcome is still going to be linear. A linear function of a linear function is still linear, right? But a nonlinear function on top of a linear function is nonlinear, right? So that's how the nonlinearity kind of captures that relationship, which linear functions cannot.
But in this particular case, you still have to label the image.
Absolutely, yeah. This is a supervised learning model. Yeah, we do label the image in training, yes. Okay, so now coming back to the session, right? Transfer learning. So how do you think we can take learning of one model to another? Does the question make sense? How do you take, so it's a model, in this case we have built it for president. How do I use that model for maybe, identifying male versus female? Can I do that? Can I not do that? Says can versus cannot. Good.
We can.
So we can?
You
How,
cannot.
why we can?
Well, it seems like that might be feasible.
Classification model.
Because you're trained for a human feature to detect the fake features.
Okay. I think we'll talk about it more, but yeah, I think your intuition is building in the right direction for now. Right? We have trained for features to read from images. Right? And we'll talk about how really this helps to transfer learning from one model into another.
If you haven't relabeled the data, you haven't relabeled the data, tell the data different, tell them all different stories, so you got different outputs.
Okay.
Assuming you're not changing the model.
Okay. When I talk about transfer learning, right, or when we talk about transfer learning, right, just like for humans, right, we learn a task, like one that comes to my mind is riding a bike. Right? If you learn to ride a bike, you learn how to balance. Not that this is true for everyone, but I'm thinking that some knowledge of it you can carry into learning driving a motorbike. Right? You learn something about balance. You use it intuitively, when you ride a motorbike, right? Now, of course, it's a different application. Of course, you do certain things differently there, but there is some part of learning which you carry from one system to another, right? As a human being. So when we talk about transfer learning, which we'll look into, right? There are reusing of model as complete reuse, to your point, that I don't change anything but reuse it as it is, versus where I can take certain pieces and parts of the model and kind of change it or fine tune it to apply to my use case. Does that make sense? We'll get into it if it does not at this point. Okay.
So are you talking about a methodology for transfer learning, or you're talking about in the sense of it, like machine learning, data learning, there's another new ways of learning or transfer learning, is there in parallel sense? Or?
No, it's not parallel to machine learning, deep learning. Machine learning, deep learning are, in different ways of, solving machine learning problems or use cases. Right? Transfer learning, I think the idea has been out there for some time, but it's really becoming popular, and we'll talk about why, right? And as you can imagine, we'll talk about it as we get there. We'll get to that question, and remind me if I forget. Like saying, right? So a few of the examples which just for you to think about, right? Like for example, the face recognition which we built, or which we saw in our previous slide, right, for identifying the president, right? How can I use that to, recognize my employees or identify my employees? Can I use that, right? Or what parts and pieces can I use? Another example is I built a model to identify sentiment classification for my product reviews. Right? I fine-tuned it, I worked hours and hours into building that model, and it's giving me right now 99% accuracy. Now I want to do it for another product. Right? How can I not start from scratch and use some learning from my previously trained model and build something pretty fast, right? To review, to get sentiment classification for my second product. Another example, you can think about tons of examples, right? Where data is related or the activity in hand is pretty much related, right? Is how you can transfer learning from one to another. Another example which I listed here is you have built a model which kind of looks at your website, university website data, and identifies the topics. Right? Now we want a model which kind of identifies all the topics in your commercial website. Now how can I use the model which I built previously for university use case for this with little training or expense?
Yeah, I just wasn't aware of this term, transfer learning, but actually there are companies already doing this. Like in Amazon, they have that recognition, the Amazon recognition, that they commercially available like AI model. You could video deploy pictures into that model, and in the back end they look it up in your database and see there's a match. That might be an example of what you're talking about.
Absolutely, absolutely. Yeah. Everything which Amazon has put out is bulk of it is transfer learning, which pretty much you can build it on your own, right? Because one of the and we can talk about it, right? The deep learning space is moving very fast, right? The models which were built yesterday is being outwitted, for lack of a better word, by a newer model which has come out today, right? So like most of the companies, you wouldn't have TPUs and GPUs and farm of servers just to do your machine learning, right? So transfer learning comes into play where models which are built by bigger companies, like whether it's Google, whether it's built by Stanford, right, which has been tested over a huge set of data, right, can now be brought in and be used by you for solving your use case, right? Anyways, so not to deviate too much from the content, I'll stay with the content just to make sure that there is clear line of thinking for everyone, right? Okay. Is it visible top? No. Okay. So we'll basically peel each part of this. So this is from. Oh, you're adjusting it, Krishna. Thank you. So this is from, like I said earlier, this is from Pan and Yang, the paper which is put out for transfer learning, right? So this kind of describes what are the different types of transfer learning we do and under what cases, right? And we'll talk about it today. Is this even visible now?
Yep.
Can you guys read it? No, not visible. Okay. So before I get into this, what do you think is the intent of transfer learning, right? Why transfer learning is useful, or why it's considered, it's pretty much considered revolutionary.
Saves time. Saves time.
Saves a lot of time, right? Absolutely cost and processing, right?
Make things easy.
Okay. What else?
Maybe your new example has fewer training, has some smaller training data, and you have more training data from the other domains.
Awesome. Yeah, exactly, right? So you may not have training data to, build your use case, right? And here is a model out there built by Google on 14 million images, with 11,000 categories. In no way you can match it, right? Now, how do I use that model, take what is meaningful for me, and add my layer to produce what I need? Right, so that's huge strength which transfer learning brings into play, and that's why transfer learning is so useful. I think for all of us here, right? Okay, so that's good. So let's get into the different types of learning, right, or different settings of learning. More than types, I think they're calling it settings of learning, which makes sense because they are not really kind of completely separate. And as I talk through the use cases, you will find out, this I heard before as well. Why does it fit here? So it's kind of overlapping at points, but we'll talk through it. So the first category is the inductive, right? Inductive transfer learning. Right now, so you guys probably cannot read it at all, not visible at all. Okay, will it become visible? I think since I should have probably.
Oh, yeah.
Much better. Just a little down, maybe.
Very clear.
Oh, almost back.
Okay. So the first kind of setting is inductive transfer learning. So in inductive transfer learning, like it says, right, the labeled data are available in the target domain. Right, so let me explain what is source domain and target domain, right? Source domain is the model from which you are trying to learn, and target domain is your use case which you are trying to solve. Right, it's the domain of the data. Okay. Now, so if you have labeled data for your use case, right? So for example, let me talk about sentiment classification, right? So like if you are a company like I am from, where we capture review comments of our customer for a product. So we have, review comments from customer. Right? I have data there, I can go in and I can label my data. Right? So if I have, labels for my data, but the case one is when I have label for my data, but there is no label for my, source data or source model data. It's a little confusing, but I'll talk about it a little more to become clear. So imagine, so in case of sentiment classification, right? Having just the review data is not sufficient for my model to classify sentiment. You know why? Because it has to understand English language to begin with before it starts, classifying the sentiments. So, like, for example, in this case, in case one, that I want to build a sentiment classification model, I can go with a model such as, BERT or ExcelNet model, which are models trained on Wikipedia and thousands and thousands and thousands of books to understand the English language, the sentence construction, the word meanings and how words relate to each other, right? So it's not trained on specific label, it's an unsupervised training model, right, which has been trained on huge corpus of text, right? And I can use that model, use that as my basic underlying model to get information from my review, for my review comments, classify them. Does that make sense? Yes, no?
You're trying to describe the text into whether it's a good mode, bad mode based on the words. That's what you're trying to do with the
Right. So my objective with my use case in hand is to be able to, my model to look at my review comments and classify whether it's, review, good review or a bad review. Right. So that's my objective. Now, for that, the way I can approach is I can go through case one, which is self-taught learning. I can use a model out there, which is already out there, like I said, Word and Excellent, and there are, more models such as these, which are trained on corpus of data, huge corpus of data. They have been trained on Wikipedia, they have been trained on, thousands and thousands of books to understand the English language, right? Right.
So these models, you said they were models, or like Bird and what are they?
Excellent.
What they're models or algorithms?
They are models. They are models. So BERT was built by Google Brain and DeepMind, right? And ExcelNet, I think it's built by Stanford and Brain together. Both of these are models which are trained on corpus of data, and what it does is, you should definitely go and read through it. Right? It is able to, give it any corpus of text. It's able to kind of classify text in a way it can, bring related words together and, can describe that relationship between words. So able to do that really well. So the point here though is not to talk about the unsupervised model, but the point here is if there is an unsupervised model which kind of, does the underlying task for you, that you can use that model and, build on top of it to solve your specific use case, in this case, sentiment classification.
Can we use both the models together?
What is both the model together?
Like the BERT and the Excellent, they're two different models, right? So can we configure it to look at both the models and
So let's
learn from, transfer learning from both the models into my.
Technically you can do.
Generally, there is not an advantage of, so yeah, I think we have to go why we are, doing the transfer learning, motivation behind it. So motivation behind this one, this case is, okay, there is a model out there which understands English language, right? Now, I can build a model for sentiment classification, but guess what? Just to first understand the English language, and for me to build a model to understand the English language is going to take a lot of, time, cost, and it's impossible to be honest. So it's out there, let me take it, let me fine tune that model and build on top of it so that it can give me sentiment classification. Right? And we'll talk about techniques on transfer learning, how do we actually do it, but that's the idea behind it, that's the motivation. That's the case one. Now let's get to case two. So the case two is where we have now label data is available in a target domain and label data is available in a source domain. So yeah, so when do you think we will do this, right? We have label data for source and label data for target. Any examples?
Voter identification.
We go ahead.
Voter identification.
Okay.
Like you have a matching. Even employee recognition, you have a database you need to match.
Okay.
That's nice. So that's good one, right? So the one which we were discussing earlier, where your use case is to identify your employees, facial recognition by employees, right? You have label data. You have list of all employees. You list, their pictures. You have label data for your data set. But for you to build a facial recognition, it's going to take a lot of effort, right? There are models which are already out there, like built on ImageNet, which I was saying earlier, right? Which is built on 14,000 million images, 14 million images with 11,000 categories, right? So you can use now models which are built on ImageNet and fine tune it to basically, solve your use case. So that's the second case, which is, where you're using where you have labeled data for both source and target, and now you're transferring, learning from known model to your model. Do you guys follow? Any questions so far?
The question is how will you do it?
Yeah, we'll talk about it. So I think I'm going the way the paper has discussed it, right? And the way the paper has discussed it is, explain all these settings. What are the different settings in which you would do a transfer learning, right? It's important. You have to be careful when you apply transfer learning because you don't want to take from a model from which there is no positive learning you can pull out from, right? And then try to find, your model because that will, if anything, that is going to hurt you, right? Go ahead.
So the model to which you are going to transfer the learning is probably built for a broader purpose, right?
That's right.
But how do you make it work for a specific purpose that you want to transfer the learning to?
Okay. We'll talk about it. We'll see some of that later, right? But remember the intuition of deep learning model, right? That's why I wanted to kind of give that intuition in the beginning again. The intuition is every layer is building on a feature. And every layer is building incrementally on the previous features. So if you were to imagine, right, like we were talking earlier, the lower layer is identifying, edges. Now edge identification, whether it's residence picture, whether it's my employee picture, both of them need it, right? Nose identification, eyes identification, right? How face is constructed, right? That learning is common to both of them. So I can extract parts and pieces of the layers of an existing model and build on top of it.
So how will you identify which layer is doing what?
So that is so that's machine learning. Welcome to the world of machine learning, where you have to do quite a few trial and errors, right? Of course, typically you kind of strip off the top few layers and you add your layers to the top. That depends on what kind of model you are picking up from, right? And how much is it related to your use case in hand. But that's a good question.
So transfer learning is really only going to work for if I'm trying to learn something that has a basis on generic. So for example, I do example review that English is pretty generic stuff. But if I'm trying to learn the anomaly data of my transactions, that's something that's very specific, right? Is transfer learning still applicable in that case?
There are many cases where you need to build your own model, right? Absolutely, right? Especially if it's proprietary, especially if it is unique, especially if you're building something differentiating in the market, you may have that need, right? But in most cases, there are models out, you can build on top of. Like to his point, right? You may not choose to extract 90% of the layer, maybe you choose to extract from the bottom 20% of the layer, right? Yeah. just giving an example, right? Based on the use case you're trying to solve, you may extract different percentage of the existing model. Make sense?
Makes sense. Okay.
Okay, the so another thing, the reason it's called, yeah, you may wonder why is it called multitask learning. The multitask learning is a unique case where based on the same inputs you want to learn different things out of it, right? And in many cases you don't have labeled data, locked labeled data for one use case than the other. Right? Classic example is like in autonomous vehicle driving, from the images which come from the dashboard, right, you have to now classify multiple different objects. You have to identify, hey, there is a pedestrian on the street, hey, are there signals there, are there lane markings, right? And for all of which you may not have, labeled data equally, but still, it's the same input from which your model can learn. So it's basically two fork of the same model. So you can still, that's where multitask learning comes into play. So this is the question you're thinking. Okay. So multitask, okay, let me try to state it one more time, right? So multitask learning is kind of variant of what I kind of said earlier, right? Which is various, label for source data, and you have label for target data, right? Now imagine a case where, let me give another example. Imagine a case where you have, face recognition model, right? So the model has two purposes. One is to recognize the face, and I'm talking about the use case. Recognize the face, and the other intent is to identify the landmarks in the face. So landmarks in the face is, like we were describing earlier, where is my nose, where is my eyes, now how far is, where are my eyelids, and so on, right? So if you were to imagine labeling of data, right, it's easy for me to label, get picture images of people, right? But it is very difficult for me to kind of label the landmark on the face, right? So I would have unequal distribution of labeled data for these two use cases. But the input source is still the same, which is right? So you can build a model where you can use it for two purposes, right? Which is one, to identify the face in the picture, and another to identify the landmarks in the face, right? You can still supply a single, same input. The benefit of this is, your model is benefiting from the same training. It is learning to discover facial features. The more you supply data, more it is able to learn. Right? So that's where multitask learning comes into play. It's an advanced concept. We can probably talk about in one of our future sessions. So far so good. So induction learning. Let's see. So induction learning is where label data is a label in my target domain. I may or may not have, label data in source domain, right? Which is my two case. Okay. Yeah, I think so these are a few examples for case one, which is self-taught learning. Again, this is from a different paper. It's by Raina. Anyways, so like I was saying, handwritten English character, you can probably use a model which has been trained on handwritten character recognition. Right? So you can build on your previous model and keep on incremental building on it, right? Are you able to relate to what's up there, to what we just discussed? Okay. Let's get into the case where label data is now available only in the source domain. Right? The earlier case was where label data is available in the target domain. And again, target domain is your domain, source domain is the model from which you're bringing the learning. Right? Label data is available in the source domain. Now, let me talk through the domain adaptation, which I think I have it here. This may be easier to understand. Okay, so this is for the next slide is for the domain adaptation, which I will talk through after I kind of talk through this example, right? So here on the left hand side, I have model which is on the lower side, right? Remove the top part of the image, assume that it is not there, this portion. Right. So I have a model which basically takes a prototype picture in and is able to classify, what object that prototype belongs to. Right, that's a model which I already have. Now I want to build a model where I can, take a picture of an actual vehicle on the road, and I want to be able to classify. So in case of domain adaptation model, even though the pictures are kind of a little bit different from each other, right? In a way that one is prototype, as another is the actual picture, right? You can still extract lower level information from your picture and build your model to meet your needs. The way you do that is, in your model, when you run your model, the model inputs or rather outputs a numerical value or set of numerical value, or numerical tensor for every image, different image types, right? So when you build your new model, all you're doing is you're trying to find out the distance between the prototype image tensor with the image tensor, with the tensor for your new image. This may be a little complex, but so any, let me see where, yeah, go ahead.
What's the tensor?
Tensor is, you can think of it as a matrix representation, right? So ultimately for the machine learning model, everything is a number, right? Everything is a number, it's generating numbers and it's computing based on numbers, right? So in this case, if you were to imagine in simplest form, right, those prototype images, for those images, based on different kind of image you are supplied for a prototype, it is going to have a representation which is called an embedding for a prototype image. So a truck prototype image will have its own embedding, right, or set of numbers to represent it. Bicycle prototype image will have its own set of numbers to represent it. Same goes for the plane model, right? So that's how your model is internally able to know when you supply any image, saying, hey, you know what, this embedding is like within the, matching close to my embedding for that prototype, and that's how it classifies, hey, this is that, image. Right? So that's the first part. So That's a basic model, right? And now, when you bring in an external, a different picture in this case, and I think I'll show it in an example later on a face recognition. That's a good example. So now when I want to build a new model, which is for image of a truck on the road, right? Of course, it's going to build a completely different embedding, right? Because the earlier model was building based on prototype. This is building based on, building based on actual images. But, when you take real images of those, in this case, different real images of those different prototypes, and when you compare the embedding difference, meaning, difference in mathematics between the embeddings, right, they kind of match. Right? So based on that learning, you can still build models to apply a real image. So this is actually, a model which was trained, like I said, on the prototype image and shown to be working on the real image. So this is an actual model which was built out, but this is the domain adaptation. So domain adaptation essentially is what? You have two different domains here. Right? One, your source domain model was only prototype data. Right? The prototype data, which is the lower side, which is the prototype picture of those vehicles. The other model's domain, input domain data is real images. Does that make sense? How your data distribution is completely different, right? Your category of data is completely different. For one model, you're supplying prototype data. For another model, you're supplying real images. These are completely two different kinds of data, right? But even with this difference, right, even with data being in different domains, you can still extract knowledge from a different domain into a new domain. Okay. Any questions? Oh, that was Brian. The second case here is sample selection bias, right? The sample selection bias or covariance shift, right?
So can you start from the start and then get into domain and then go to the sample selection?
Meaning?
So if you start from transfer learning, finish your domain and then go to the sample again.
Oh, this here?
Yeah.
So transductive learning is the second category of, or second setting of learning we are talking about, right? And within that, there are two categories. One is domain adaptation category, which I talked about, where your data domains are completely different, right? One was a prototype data domain, another was a real image domain. The second example is a domain may be very close.
Real doesn't have the label.
Say it again.
Real images didn't have the label.
Real images didn't have the label, absolutely.
They had the label.
No.
No.
Yeah. So if I haven't called it out, yeah, exactly. The real image doesn't have the label. Right?
So that's the difference between this and this.
That can be one of the cases, but more importantly, even if it has label, you can take learning of a model trained on a different domain and bring it into your newer domain. Because the extent of training, like we talked about, the advantage of transfer learning is you don't have to train your model to the extent which is needed. Right? Okay. Good call out. So the selection bias, right? The selection bias is a case which I think you will get it individually. Domain adaptation is kind of a little complex, but go ahead, shoot.
Can I ask you questions regarding domain adaptation?
Right.
What would be the use case for domain adaptation? Why would I take the domain of pictures of the cars, not non-real picture like Toyota cars, while I can I can fit the real picture of the cars into the model as an input. What would be like real world use case?
Okay. So you know the example. Another example I'm thinking about is like ImageNet example. Let me give that, right. So the models, there are a lot of models which are today built on ImageNet database, and for those of you who do not know ImageNet is a data set, like publicly available data set, which is, like I've been saying, 40 million images, more than 11,000 categories, right? So there are models out there which have been trained on that image. Okay. Now that's trained on images, so it has all kind of images, right? All animals, all 11,000 categories. That's a huge data set. So if you were to imagine that data set, that data set distribution is really big, right? Now, if I want to build a facial recognition model, right, which is kind of a different domain, right? So I want to build a facial recognition model for all the people in the room, such that when I supply your picture, it should be able to tell me, or it should be able to say, hey, it's you, right? If I supply your picture, it should be able to tell it's you, right? So if you were to imagine this domain, this data, distribution is different than the data distribution of ImageNet. But ImageNet has been trained on lots of images, so it knows how to read, go through the edges. It knows how to identify, blur, light, dark, day, the different ways you can stand, right? So it has learned on all of those behaviors or learnings. Now I can extract those learnings from that model, and can bring it here for my problem. Do you get how powerful that becomes?
Yeah.
Because now it's solving a different problem there, but I can take part of that model and apply it to a problem here, which is not, related. Right? So the first case was where the data domains are related. The second case is where data domains are not related at all. Right? They're completely different. I think good that you asked. That helps me to explain it in different ways.
Yeah.
Go ahead. Shoot.
And this is all unsupervised learning, so I don't have to retrain.
This is all unsupervised. Elaborate that.
Like I'm asking, so it can do it can do recognition or image recognition on the 11,000 categories, but so then when it comes to the people in this room, I won't have to retrain it. I can just apply the facial faces and then we'll be able to know.
So that's a good question. I will have to retrain it to a certain level, or at least so in this case, we are trying to build a model which will identify every people in this room. So I will have to supply pictures with labels of people here in this room, but I don't have to supply your picture for every possible combination of image which that model can see, right? It may be under a light, maybe close, maybe far, under sunlight, moonlight, and so many other possibilities, right? So I don't have to train my model for all those cases, because the model which I am transferring my learning from has been trained to recognize all of that, right? So that's the huge learning we take from a different model. Make sense? Good? Okay.
So this domain adaptation will take more time compared to the one which, because both are not correlated.
Good. I think that's that's nice. So if you were to think about transfer learning in general, right? If I can take a model and apply it directly, if the model I can use 100%, that's the easiest thing to do, right? There's a model out there and I want to do a similar task, I take it and plug it for my name, that's the easiest thing to do. The next thing, next level of difficulty, if you were to imagine, hey, model does 80% of what I need, it needs to do, I need to, add another 20%, I can take that 80%, right? Then, domain adaptation is where, hey, I really don't have any model in my domain, but there is a model which does that, which identifies text for me. I now want to, create a summary for a book, right? I will probably take that, right?
And in continuation of that, again, this will become like a new model.
Absolutely.
For new case.
Yes. Yeah, good point. So I built this model, now this model is that model, which can be built upon further. Yeah, good call. Anything else? Okay, that's good. Good discussion. Yeah, I think discussion really helps. Okay, so covariance shift, right? We were talking about the covariance shift. So this is another kind of where domain is a little different. But unlike domain adaptation, where it was completely different, covariance shift there's a little shift. For example, if I have a model for the population on which I have trained, I'm trying to predict their life expectancy. That's my model, okay? And guess what? The population on which I trained, there were very few smokers. Now I take that model and apply it in a different country where percentage of smokers are really more, right? Then that model, if you think about the data distribution, the data distribution has changed, right? I didn't have as many smokers, for the model for which it was trained. In the new setting, the data distribution has changed, right? But as you can imagine, there's still a lot of learning I can take out of the model and train for my new setting. Does that make sense? Okay, so that's covariance shift, but broadly, these are two areas where there has been a shift in data domain or data distribution. Okay, so this is unsupervised, right? Which I think you were talking about briefly, right? So this is a case where there is no label data in both source and target. Right? Let me say this: the usage of unsupervised is, at least other than the research purpose, is very low in the industry right now. Right? There are cases where you can apply like anomaly and clustering of customers and so on. But generally, the utilization of unsupervised learning is much low in the industry. But so this kind of transfer learning is where you build incrementally on your unsupervised learning which you have done before. Right? I think a good example of this may be the good example of this we were to imagine is the text, like we were discussing earlier, models like BERT, which are unsupervised, which are trained on Wikipedia and huge corpus of data. Now, if you were to build sentiment classification on, for any huge corpus of data, you can possibly use BERT as an underlying source model and build on top of it, and which is how it is happening. The models like BERT are built on the previous. But bottom line, this is a setting where you take an unsupervised source model and build on top of that an unsupervised, target model. So those are the different.
So you're saying first BERT learned the English, right? And it was unsupervised to figure out the relation and how all word and character goes together, right? Then you put the sentiment on it. It classifies sentiment like this is a bunch of sentiment, this is a bunch of sentiment, this is a bunch of sentiment. Doesn't know which is good, bad, or what.
Yeah. And you can think about it. You can build incrementally on top of it, right? As much as you want.
And one question: what period of time this unsupervised will become supervised? Once you find you
have more labels.
Have more labels.
Unsupervised will become supervised.
like suppose once you identify this clustering and all, you will have labeling for the customers, good and bad, or you can able to categorize. Can it be, my question is, like, can it become like a supervised learning or build up and also the model fine tune and it got identified?
So supervised learning is where you supply data with labels, right? That's supervised learning. Unsupervised learning is where you don't supply label with your data. Of course, there is learning which you get out of unsupervised learning. Like to your point, output from an unsupervised learning can be clustered. You can, like we do, we segment our customers based on their spend, right? What customer segmentation does this customer belong to, right? So we are able to do that with unsupervised learning, right? But there is learning, but I'm not going back to label my data as the point. Okay, I think this is a few questions which running on time. Oh, okay, go fast. Yeah, the transfer learning solutions, right? These are actually the 4 different ways to do a transfer learning. Out of which I will say outright, talk to the feature representation transfer and parameter transfer are the ones which are commonly used. We'll talk about it. So feature representation transfer. Like we were talking about earlier, right? If the deep learning model is built out of 10 stack layers, right? I can extract maybe 7, maybe 8, or whatever number I want to extract from that model, and I can plug it, and I can plug my layers on top of that layers to build my model. So that's the feature representation layer, right? Where essentially you're taking features from the learned model and you use those feature representation for your model. You don't change the model underneath at all. Does that make sense? The parameter transfer, on the other hand, is you bring in an existing model. But the existing model is, so let's take an example, right? The ImageNet model, right? It's able to classify, like I said, 11,000 categories, right? That is already built. That model is built, and that model has features, right? Meaning if you supply a picture of cat, it's able to tell you it's a cat, right? And the way the model does it, which we talked about in the last time, is the layers in between has something called as weights, and those weights are trained in such a way that now you can supply the image and it's able to classify the image, right? So in parameter transfer, what you can do is you take that weights, that's your starting point, and then you start training that model with your data. So your parameter of the learned model is changed. So the difference between feature representation versus parameter transfer, to put it simply, one is feature representation is to take the model as is and build on top of it. And parameter transfer is you take the model, you take the learned model, existing model, and kind of fine tune that to your use.
They sound one and the same.
Say it again.
That sounded pretty much the same. Can you repeat?
Okay, yeah. So feature representation transfer, right, is where you have an existing model, right? You just add your layers on top of it. You don't retrain that existing model layers. You just take them as it is and put your layers on top of it. You train your layers, but you don't train the underneath layers. That's feature representation. Parameter training transfer is you take an existing model, you add your layers on top of it, right? And then you train, but you also train some of the layers of the existing model. So in a way, you're fine-tuning the existing model. Make sense? there's subtle difference. But those are the two popular ways, the two common ways I should say, we do transfer learning solution. Relational knowledge transfer is pretty much, I think we talked about it lunch one other thing, it's pretty much where, you know, you, like I was saying, BERT, which is able to understand data, right? Since it's trained on corpus of data, now you can use that for sentiment classification. You can basically take that and apply. So it's where models are, operating around the same relational data. Instance transfer is complex. It's a little complex where you adjust weights based on the weights differences. So I'm not going to get into it. It's a rabbit hole if I start getting into it. Stay away from that. But instance transfer is not that common, because it's intuitively prone to error. Where you are trying to adjust the weights based on
the outcome.
Existing model. That's intuitively prone to error, so we usually don't do it. But those are the different solves which we can apply, or those are the different ways in which we can learn transfer learning. If this helps, this is another way. Feature representation and parameter transfer, to your question, right? If you were to look, so feature representation is on the left hand side, right? Existing model, you're cutting it off, you're putting your layers on top of it, boom, you're done, right? The parameter transfer is on this side, right, where you take a source model, you come down, you can freeze certain layers, and you can fine-tune certain layers, right? So those are the two common ways where you do transfer learning.
So ideally, you will always start with feature representation, and if it's not for your satisfaction, then you will get into parameter transfer. Will that be the approach, or what will be the result of that if you go to the parameter transfer?
I think it depends on the use case. If your current model almost satisfies your need, then you can just add your layers and start, building your model. But if you think that your current model needs to be tinkered, that's when you can go into parameter transfer where.
No, but that's a good call out. You can approach it that way. You can start with feature representation and then go in and freeze or unfreeze layers. Right? Yeah, you can do it. Yeah, but it doesn't necessarily happen. Right? If you understand your use case better, the domain distribution is a little different. I would rather train it than use it as it is. Right? So it's certain judgmental calls you have to make.
In practice, how do you do it?
Well, in practice, yeah, we'll show.
In practice, how do you cut out the layers in your original model and your own model, or your own layer to it?
Okay. So that kind of, I think takes me to the simple demo, which we will see. Oh, I realize this is your computer, not mine. Good.
How will cast it?
The models are built on top of it. So what I have here is a very simple face rec. API probably I should keep it smaller.
Command minus minus.
Any better? So this is also I posted it on Medium, so you can go into Medium and find this article there. What am I doing here is I'm taking an existing model, right? Which is I think in this case I have taken Inception. I think Inception ResNet, if I'm not wrong. Yeah, Inception ResNet. So I've taken an Inception ResNet model, which is an existing model, part of Keras package itself, right? And it is trained on ImageNet model. The Inception ResNet was a cutting edge model a few years back, trained on ImageNet model. So what I'm doing here in this code, I'm taking that model. I'm doing a feature representation here where I'm taking that model's feature out of it, and I'm using it to solve my face recognition. Right, so I have two use cases, simplistic use cases at this point. Of course, it doesn't get into a lot of complexity, but it solves two use cases. One is verification and another is recognition. So the difference is verification is basically identifying this person is that person. Recognition essentially is I'm going against a database of pictures and saying, hey, is this my employee? Right. So, anyways, okay. So to quickly, so here I'm importing quite a few libraries. I don't think I need all of them, but so this, what is it I'm using, Crystal?
Jupyter.
Okay. So okay. So this is the model, right? So all I'm doing is, like I said, Chaos has Inception ResNet already, right? So I'm just taking Chaos model, Inception ResNet model, which is pre-default. So like I said, it's already trained. It has all the weights set already. It is trained on 14 million images, 11,000 categories, right? So I'm using that. Load, not yet. So it's running. I go for, okay. Good. So, yeah, let me run this again. So if I do a model summary, it shows me different layers of the model, right? So this model has so many layers. Right, so there's a lot of layers. There's been, it's pretty dense layer, right? If I were to build this model and train this, imagine what kind of computation power I will need, how much time I will need, right? So take that, and all I'm doing here is, if you look at the last layer is prediction layer. Right, so all that last layer is doing with ImageNet is it is identifying, hey, it's a cat, hey, it's a dog, hey, it's a human being, hey, it's a car, hey, it's a truck, or whatever, right? So it's, the last layer is essentially putting, classifying what the image category is. So I'm going to strip off that last layer. I don't need you to classify me, for me, cat, dog, whatever, because I want to use it for a different purpose, right? So I'm stripping off the last layer just by saying to your question, right? Base model.get layer, what layer I want, right? So in this case, like I was saying, I want to get the last average pool layer. So I'm just applying, saying, hey, give me the average pool layer from this model, meaning all the layers before the average pool. That's all I'm saying, and it's stripping off. Right? So now I have a model which doesn't have a top layer, prediction layer. It has everything underneath it, right? And in my case, all I'm interested is to get representation of the image for my face need. I don't need to classify it. All I need is representation of image. Like I was saying earlier, every image has its representation, and that representation is sufficient itself to identify what that image is. Okay? So what I'm going to do, if this makes sense to you, right? So I'm going to calculate representation for, if I were to do for this population here, I'll supply your picture to the model, right? Maybe one picture, right? And I'll get a representation for each one of you here. with the model outputs, right? And I'll probably store it in a database, saying, hey, what's your name?
Seon.
Seon. Did I say it right?
Yeah.
Okay, Seon. So this is the representation for Seon, right? Another for Krishna. Hey, this is the representation for Krishna. I'll store it in my database. Next time, when anyone comes in, I'm just going to take that image, compute the representation, and compute that representation's difference with what I have in the database. And if it is matching to one of the representation, I can confidently say that this is the same person. Does that make sense?
Yeah.
Okay. So, yeah. Let's see this page. This is all just pulling. So I'm just getting the picture from the wherever I showed, showing it here. This is all.
That model has so many layers, and then it comes to the question like, which layer are you strip of the original model, add your layer to, or you just keep adding your layers to it.
Right.
Like you said, I don't know how many layers, maybe hundreds.
Yeah, definitely. There are more than 200 layers,
Right.
240 layers.
But how can I understand that many layers in that model? You know which one to strip off.
Very nice. Good question. So the whole purpose of what we discussed earlier, was to identify, what was your source model doing? What is your target model about, right? If your model domain data comes from the same distribution, then you can pretty much use the entire model. I think you asked me that question earlier, right? If my source and target domain data are like stretched apart, like for example, one is from prototype, whereas another is from a real image, I'm probably going to extract some lower level layer, maybe 30, maybe 40, and some layer I'm going to strip it off. Right? So how closely is my domain data distribution for my domains? Based on that, I'm going to take the layers. That's one part of it. Second part, which is usually the case, is you have to, trial and error, right? Which is why model building takes a lot of time, right? You try and, try. Let me go forward here. All right. What happened?
The first one, before that not running. Because you have to run that one.
Model not for.
Because you jump the step.
Right.
Yeah. No. Okay. No. Yeah.
Yeah, I think I want to run the model. Okay, so in this step, what I was saying earlier, I'm reading it and I'm storing it in the database dictionary. Right, the encoding of all this image. You guys are following so far?
Yeah.
No? So what I did here is I have some 9 or 10 different images. Right, I'm reading it, generating the encoding, and storing it in a dictionary. Right, those are my employees. Right, so I come down here. So this is a basic function. All it does is, now you supply a new image, it generates the encoding, it does a L2 norm comparison between the encodings which you have in the database versus the new encoding which you have supplied. So L2 norm, essentially you can think of it as a difference between the embeddings or encodings. And if it is too close, then it's going to say, hey, this is that same person. If it is far apart, it's going to say, no, this is not the same person. Right, so that's the verified. So I'm supplying a different image, right? So my earlier image, if you were to see here, the image which I put in the database is this. Is it visible? No? Okay. Right, the image which I put in my database as an employee is the one above. Now, when I'm testing it, I'm going to put this image. Right, this image. This is a different image. I didn't supply to the model level this image, right? But since I'm using an existing model, which has been trained on all kind of different image combinations, it's able to detect that this is the same person. Right? So it's saying, hey, it's Lijesh, welcome in. Right? Now, if I supply an image which was not in the database, like this guy is not in the database. So now let's see what it does, right? Basically say, hey, it's not him, go away. Right, so when I supply image, I also say which person I'm calling myself, right? So just checking for that specific person in this case. So this is verify use case where I'm checking an image against a named person, right? Now the one below, which is simple, it's a facial recognition. In this case, you supply an image, it's going to compare with everything in database. It's going to say, hey, this is that, one of my employees, and it is this person, right? If it doesn't find in the database, it's going to say, hey, it's not of my employees, right? Again, this.
I have a question.
Sure.
So the second image that you gave, are you going to store that so that next time?
No, I'm not sure.
You're not storing.
Yeah, model is smart enough to know, that this is the same person because it was trained on, use set of images. There's no need for me to store. But that's a good question, yeah. Yeah, but there are other models where you store and it kind of adds to your, knowledge.
Right.
Yeah. So let's see. Okay, so supplying an invalid employee. So it says, hey, I didn't find you in the employee database. So it's a simple, use case. It's available, like I said, in Medium, and I think I posted the link in the Meetup. You go in and check there and look at the source code further. But like I was saying, extracting parts of layers of model is very simple. It's a line of code in Keras. But understanding the concept is important. More importantly, when your question earlier, when should I take model or existing model? How many layers should I take? In what context it makes more sense to take, the entire model versus, part of the model.
So just curiosity, if the original model you're using, that model has been trained on how many images?
It is trained on ImageNet. So ImageNet is, I think last I checked, it was 14 million images. 14 million. 4 million, yeah, 14 million.
So is there a cost to use that?
No.
It's open?
It's free, yeah, it's open. Everything's open, yeah. So, yeah, to your point, right, we were talking about earlier, like if you think about Amazon or some of the APIs out there, underneath they are using those open source models.
So in a real world, and probably they might be tying up this program to a door so that automatically when it comes, it's open the door.
Yeah, I know a couple of years back. In fact, this comes from the FaceNet paper, right? The idea of comparing, embedding settings was first put in FaceNet. That's a paper we published a couple of years back. So this was implemented by Baidu. So what Baidu has, Baidu is in China, right? What Baidu has is there's a face recognition, camera in front of its employee entrance. All you have to do is just walk in, it will just open, right? And that's built on this premise. Okay. And any other questions? Otherwise, thank you. Thanks for coming in. Have a nice rest of the evening.